A little bit about our panel members. We have with us Kirby Ikin from the Australian-based GIO Reinsurance Company, Walley McClure, who is an engineer with Rockwell International. And we have Dr. Raymond Bula from the Wisconsin Center for Space, Automation, and Robotics. First about Kirby. Kirby is responsible for space business development with the GIO Reinsurance Company. Since its entry into the insurance market in 1986, GIO Reinsurance has become the largest risk insurer in the Southern Hemisphere. Also, in his GIO capacity, Kirby is director of the joint venture company SpaceGuard. SpaceGuard provides unique services in the provision of orbital debris hazard analysis and aerospace insurance companies worldwide. Kirby is also a member of the National Space Society Board of Advisors and has been president of the Sydney chapter for more than 6 years. He is widely recognized as one of the key movers and shakers in the Australian space community at large. Walley McClure has been involved in space activities both as a professional and a private citizen. He's been involved with the marketing of space launch services, design analysis of manufacturing of space hardware, commercial investor groups interested in financing commercial space ventures, looking at various private-public investment strategies, and so forth. Most recently at Rockwell, he has been the engineering team leader on the extended duration orbiter project, privatized the project to allow the shuttle to stay on orbit for multiple days, and so forth. And he's been very involved with the ACRV lifeboat for the space station program and other programs of commercial relevance at Rockwell. Dr. Bula is a co-principal investigator of the astroculture project of the Wisconsin Center for Space Automation and Robotics, which is part of the NASA Office of Commercial Programs network of Centers for the Commercial Development of Space. Doing so, he's been doing this as a professor at the College of Engineering at the University of Wisconsin in Madison, and has formerly served as the executive director of the Wisconsin Center for Space Automation and Robotics. He's had a leadership role in the WCSR spaceflight hardware development program for the shuttle and for Space Station Freedom. And so, because time is short, I'll get on. Kirby Ikin.
Thanks, Jordan. It's a pleasure to be here again. And I just say again, this is the third conference that I've been to in a row, and it's a tremendous pleasure to have the opportunity to speak here. In fact, I can see some familiar faces in the audience, and some of the people here, in fact, there's one person in the audience who's probably heard me say some of these things twice in the space of about a year. I do apologise to them. This isn't a rehash of talks that I've given in the past. They will probably see some common ground. Given that we're talking about commercial opportunities in space, there are three particular projects in Australia that I want to discuss today. And I am conscious of the fact that time is short and the fact that I have another commitment at 5 o'clock. So one of the reasons that we've had to change the structure of the panel is because I have to leave before that 5 o'clock meeting. So I do apologise in advance for perhaps speeding through these things. And if you don't have time to ask questions that you want to, I'll be around for the whole conference, and please feel free to speak to me. Most of you would probably have an inkling of Australia and its size and the lack of population and so on, so I won't really go through those kinds of things. But some of those characteristics are pertinent to remember, in particular the fact that Australia has only a population of 17 million and a land mass almost as great as the United States, and that gives us certain advantages in certain fields of space, in particular launch services. One of the other key things that I want to point out about Australia is that we don't have any massive federal government space program, and hence the space companies in Australia have grown up with a fairly different kind of philosophy and approach to things. By and large, they're more willing to look at programs in a purely commercial sense and not to live off government programs. And I don't mean that in any demeaning sense with respect to the US or European or other companies. It's just trying to set the scene for the environment that we have in Australia. The other thing that I quickly want to point out is that in a commercial project and a commercial opportunity, there are many things that make it such, other than just having a good product and maybe a clearly defined market. There are other things such as political advantages, cultural advantages, geographic advantages, which is probably one of the important things in Australia, and even questions of security and stability, all of which can, when brought together, make a project commercial. And I want you to bear those things in mind as I talk about these Australian projects. The first one is, of course, the Cape York Spaceport proposal. I've come here 2 years in a row now and spoken about that project, and I think many people who've heard me speak before all believe the project is currently dead because they haven't heard much about it in the press. Well, it's certainly not dead, though I must say it hasn't progressed a long way in the course of the last year or two. But there are things going on, and I'd like to give you a very quick sort of update on its status. The project, for those of you who don't know, is basically to build a launch facility in the far north of Australia, on the Cape York Peninsula, to launch communication satellites into geosynchronous orbit, and basically to produce a similar service to that operated or offered by Europe and by the US, the various US manufacturers, also by the Soviets, or former Soviets, and by the Chinese now. The concept in Australia is built around use of the former Soviet Zenit launch vehicle, but it is no longer confined to just offering the Zenit launch vehicle, and that's one of the key differences to what I might have been saying a year ago. There is a consortium or a group known as Space Transportation Systems, which is progressing the project at the moment. Their idea, while it's built around the Zenit as the core vehicle, they're interested in offering a total range of launch services to make it a truly international facility to anybody who wishes to use it. And you may say, well, what's the advantage to the likes of, say, McDonnell Douglas or the Chinese or any one of the new Soviet republics to come to Australia and to launch a launch vehicle there? Well, if we have the full facility built around the use of the Zenit, then it becomes quite reasonable and cost effective for any one other manufacturer to build a dedicated launch pad and to utilise all the existing infrastructure of a spaceport. So it becomes reasonable to assume that perhaps General Dynamics or McDonnell Douglas, perhaps the Indians or the Chinese may have a rationale for building a dedicated pad at Cape York. Now, the political scene has changed somewhat such that we now have Intelsat wanting to purchase a Chinese launch, and Inmarsat hoping to bid for or to have a Proton launch in the future for the next series of satellites. Those things obviously diminish the commercial rationale for doing Cape York. But if you'll bear in mind my earlier comments, there are many things that also make Cape York still a potentially viable project. One of those is the geographic advantage. With the Zenit vehicle alone, you can virtually double its payload capability if you launch it from Cape York as opposed to from the former Soviet launch pad. There's also the question of political stability and security. And if you're a satellite operator and you were contemplating perhaps what is now on the foreseeable horizon of a Proton launch from the Soviet Union, I would still have grave doubts about whether in 2 years' time there would be sufficient political stability to allow the launch to go ahead. That's something that can be guaranteed in Australia. And lastly, there are sort of political and cultural advantages to a neutral site such as Australia. There are many countries in the world that, for whatever reason, may prefer not to deal with either the Soviet Union or with the US or with Europe, and who may well find a relatively neutral international site in Australia quite attractive. If the project goes ahead as planned, then the first launch would be possibly late 96, more likely early 97. Now, while I mentioned that this group, Space Transportation Systems, has been taking the project ahead for about a year now, literally the day before I left Australia, which was about 3 weeks ago, a new group emerged on the public scene. Most people have been aware that they were there in the background. And it's a combination of a Dutch company with the initials HBG, which for the life of me I cannot remember what they stand for, and an American company known as Kirby Corporation, which managed the Johnson Island missile test range, who have waded in to the bidding and would like the Australian government to rescind the mandate that STS has to take Cape York forward. And if that mandate is rescinded, then they say that within 6 weeks they will commence the environmental impact study. So you can see the project's not dead. It's by no means a dead cert that it will go ahead, but it's still got life in it, and I think it still has certain commercial merit. The other current project, which I personally find more exciting and perhaps with greater true commercial potential is for a small launch vehicle to be built in Australia, or perhaps more appropriately in its early stages, assembled in Australia and launched from Australia. The project originated as the Australian Launch Vehicle Project back in about 1987, and the team went through various generations and evolutions, but we now have a new consortium which is operating under this new title of the Southern Launch Vehicle Program. And that group consists of British Aerospace Australia, Hawker de Havilland, which is a subsidiary of Hawker Siddeley, and Ozspace, which is a 100% owned subsidiary of Matra Marconi Space. So you can see that all of the players in this project have good heritage. They're all space companies, they have large aerospace programs in Australia, and their parent companies have very significant space operations internationally, which gives them a certain critical mass which the original project lacked. They're currently working under a $1.5 million concept definition study funded by the Australian Space Office, which is loosely the equivalent of NASA in Australia. And the definition of the project as it stands is for a small launch vehicle capable of placing 1,500 kilograms into low Earth orbit, which gives it quite a significant ability, I believe, though I could stand to be corrected, greater than Taurus, and certainly greater than the Scout, I believe. So that's the kind of lifting capability that they're after, and of course the principal market is the LEO, the low Earth orbit ComSats, the likes of Iridium, Ellipsat, Odyssey. Now, all of those have yet to prove themselves as real projects, though I think most people in the industry, and I guess I use my space insurance background here to some degree, foresee that there is going to be a market there. Just what that small satellite market will be is undetermined, but there's a great deal of potential there. And those small, the LEO ComSats would be launched into polar orbits, and hence the vehicle would be launched from the Woomera test range in South Australia, which was an active site 20 years ago, has much of the equipment still down there for relatively simple launches such as this vehicle would be, and has the potential to be reactivated fairly quickly. However, this 1,500 kilogram to low Earth orbit capability also has significant potential for the likes of re-entry capsules. Now, the other very exciting thing about the Woomera site is that it is quite probably the best re-entry range in the world. It is a very vast site, a prohibited zone, which in itself is important because you don't have to go through the process of establishing it all, it's already there. And you can safely re-enter a capsule into Woomera, and you can miss by several hundred miles, and I dare say even 1,000 miles, and you're not going to come anywhere near anybody. And that's quite significant, especially from the space insurance point of view. That provides extra levels of comfort and safety. And if you're a European manufacturer or a Japanese or Asian company that wants to do some microgravity research, then you have no inherent desire or need to land in the US, and hence the availability of a good site in Australia makes it quite commercially attractive. As I've mentioned, there are geographical advantages to the Woomera site, and one of the other advantages that I think is not to be underestimated is the ability to streamline the regulatory process for both launches and for re-entry. I was speaking to a company that's in the sounding rocket business only a couple of days ago, and they were telling me that to conduct a sounding rocket launch from White Sands, and this is only a sounding rocket launch, costs $150,000 just in fees and paperwork. And that in fact, some of the people at White Sands told them point blank that the regulatory process is set up to almost specifically put off commercial launches from the site. Now maybe that's overstating the case, but that's certainly the effect that it tends to have. And one of the other advantages that Australia can try and grasp is to come up with a very streamlined regulatory process. You have a good site, you have a launch vehicle, you have a politically neutral country. Altogether, we come up with a total package which makes it attractive and commercially viable to develop a small launch vehicle from Australia. Now that project will definitely involve an international partner and almost certainly an American company. And the Southern Launch Vehicle Corporation has been talking with Lockheed, Thiokol and Amarok. And from all reports that I've heard, there's been a very great deal of interest from those American companies. It remains to be seen just what joint venture, if any, should come about, but it's certainly looking attractive at this point in time. The first launch, if the project goes ahead, would probably be in 94, early 95. Given the scale of the project, I think that's achievable, and also given the fact that there are other small launch vehicle products coming onto the market or mooted to come onto the market, I think that sort of gives an extra imperative to make the project move pretty quickly. Because I see we're certainly running out of time, I'll make one last quick project, talk about one last quick project, which is a longer term one for Australia, and that is the development of an expendable scramjet. Australia is quite possibly the world leader in hypervelocity shock tunnels. The University of Queensland, in fact, is probably the world leader in that field and has been contracted to build such shock tunnels in various places around the world, including one for a rocket tunnel in the US. Part of the research that they have done in these shock tunnels is towards the development of an expendable scramjet, and the project is designed around developing a throwaway stage that would become the second stage of a vehicle, say the class of a Scout. One of the big problems with a scramjet is generally materials technology, and by pursuing the route of an expendable vehicle, it simplifies the technology requirement, the materials technology requirement quite substantially. As I say, the vehicle is really designed to be a second stage on something like a Scout, and if you can believe what I've been told by the University of Queensland, they believe that by using this second stage, you could probably double or possibly even triple the launch capability of such a small launch vehicle. The attractive thing in all of this is that the cost to continue the development of this project is only on the order of $10 million. Now that's not a great deal of money in the space field, and it's certainly something that's quite conceivable in Australia. Thank you very much, and please excuse me for hastily rushing out at this point. If anybody does want to catch me, they think of something later on, as I say, I will be around, and I'd be more than happy to answer any questions that you have. And just a plug, if you're interested, there's a magazine called Space Digest in the room almost opposite, which is free for people to take, and that might give you a little bit more background about what's happening in Australia. Thank you.
Thank you, Kirby. Now, why don't we have Walley McClure from Rockwell.
When I talked to Jordan about this, he asked to make a modular briefing, so I'm going to abbreviate this briefing down somewhat. So, Randy, could we go over to page 3, chart 3? The original title of this talk was to talk a little bit about space commercialization and some of the impacts we might see, both pro and con, and some of the future for some of the space exploration activities. And to sort of start off on this, I'd like to use George Santana's definition. Those who don't understand the past may be condemned to repeat it. The counter-argument to this is projecting future space markets is sort of like trying to estimate the demand for a bridge by counting the number of people who swim a river. It's an area in which you can lie with statistics very well. So I'm going to try not to be too wild in my claims and try not to be too conservative in my assumptions. There's lots of definitions on space commercialization, and I've sort of used a fairly loose one. The best one I've seen is the one from Presidential Commercial Space Policy Guidelines. Anybody who's in here for Courtney's excellent talk this morning on commercial space, and I'm going to be showing some slightly different numbers than he has. I have some updated numbers that's a little bit more recent than what he has. We go over to chart 5. If you want to look at who's spending money on space, sort of give us an idea where all the money is coming from and where we might see it going in the near future. There's that large bar on the left is the U.S. government, and following somewhat behind them is ESA and the European community through both national programs and ESA. Also, the Japanese space program is ranking up in there. Then over to the right, you're starting to notice a couple of new things showing up on the horizon called U.S. commercial and foreign commercial. Have the next chart, please. However, if you remember that definition of what commercial space activity does not preclude somebody from making a product and selling it to the government. And as a matter of fact, if you look at what the U.S. government is buying in space products, you'll find that about 75–80% of their stuff is money that is not going to government employees. It's going to contractors to provide services or products to the government. And if we can skip over to chart number 8. And we go beyond that, we start looking at what U.S. commercial space activities are. You can see that we're looking this year at about $4.4 billion in U.S. sales of space products. The end of this year, we're estimating about $5 billion. These numbers are a little bit higher than the ones Courtney showed this morning. They're based on a little bit more recent data that's being circulated in the industry. However, if you'll notice that most of that market is really associated with communication satellite services of different varieties. Part of this is an area in which there is a much more mature market and an area in which there is a lot of current activity going on with a lot of companies out there. Next chart, please. If you want to be, say, you can lie with statistics. If you take what we've seen over the last 5 years and sort of start plotting some numbers through it, you can see if we're looking at what the historical growth rate is, we're going to hit substantial revenues within a very few years. And if you just plot a straight line through it, which is probably not too realistic either, we're still going to hit probably we're starting to approach a very reasonable size space revenues, again, by about the end of the century. So this is a near-term market that's substantial. Not too many people realize that this is a $5 billion a year business in the U.S. in commercial space products and activities, and in Europe and overseas, you're talking probably another $3 to $4 billion. Numbers there aren't as good. Could you skip over to chart 11, please?
Does that include revenues from contracts?
Yes. Also the revenue from sale of ground stations. Probably the biggest change we see on the horizon that really isn't factored in this, and this is sort of a weather change in what we're seeing in the market, is if we see some expanded space exploration activities or some variety of the space exploration initiatives that we talked about. The reason this is probably so important is that it is becoming a centerpiece of the government policy. It's becoming a focus of a lot of government activities. It still has not been well defined. So there's a lot that we can do to sort of define it and define how the market's going to be set up. And if you go back and even look at the Stafford reports, there's a lot of commercial potential. Furthermore, this is an area, because it's new, can be used as a method of reforming some of the practices we do now and defining how we're going to do business in space in the future. Could you skip over to chart 13, please? And some of the methods we can use in this are, we can go through government action, go through procurement reform. Some of the things that have been talked about, and there was some discussion this morning about revised procurement process, authorization of pilot test programs allowing us to do some procurement experiments to see what works and what doesn't work, meeting the goals. Termination of liability, which really begins to reduce the risk and start increasing the comfort level of a lot of the financial backers. And there's a variety of other things that you can look at. Similarly, when we get into these projects, one of the things that we've ignored in the past are dual-use technologies. In other words, let's emphasize the technologies that have a direct market application as well as a government application. And also encourage commercial participation. And probably the best point on that is that bottom line. You need an open door and open mind policy. If somebody wants to come in with something that looks something that may not be exactly what the government has in mind, but he thinks he can make money on a commercial. It's something that should at least be looked at and should be considered as part of the planning process. Similarly, when you start planning for these projects, you have to very early start thinking how we're going to take the technology or the products or the systems out of the government and transition them over to the private industry, both for operation and also to maybe see if there's some commercial products that you can find out of this. It's something we really need to increase as part of our current planning. There's a variety of ways that we can do this involving the government. This is sort of a Chinese menu listing different ways you can do it, maybe some applications. There's off-government financing. I've been associated with a project in which we've built some major pieces of space hardware and delivered to the government. We've financed them on our own, built them on our own. We give them to the government. The government pays us what we spent on it. But all the money we spend financing has to come back out of use of the system by non-government users. Now, for major pieces of space hardware, major programs, this is probably not the best, but it is one method of getting some systems online areas and tapping some financing sources that are not that common. There's a variety of areas you can apply it in exploration. Unmanned precursors. There's a recent project done through OSC and Goddard Space Center called CWITS, in which OSC will build and launch a ocean observation satellite. In return, the government has promised to buy a certain amount of their data. However, to make the commercial venture work, and back to those policy guidelines, the government cannot be the whole market. You've got to find enough commercial users to make it a reasonable, viable commercial venture without depending solely upon the government. Similarly, there's a combination of joint government and industry financing, in which after it's developed, the private industry operates or the government leases the system. You've seen discussion of this in CDSF and in a variety of other programs. There are a variety of applications. As one example of this would be like a space transportation system operating between here and the moon, or operating between here and Leo. If it is a system which is primarily designed for government requirements, for which there are some other commercial applications, you might be able to work a co-financing arrangement, which would then allow you to go out and jointly operate a system, using the government basically as a source of venture capital. They've got deep pockets and a low hurdle rate, so you might be able to get some financing applications that way. Similarly, the government can just buy services. Say, I want to buy X amount of data about the moon. I don't care who puts it up. You come in and tell me who's going to do it, and I'll write you a contract for gathering X amount of data of this type over a certain period of time. This has been proposed for some of the near-term systems. You can also see it directly in the space transportation, the launch services, and you can see it potentially even in some system elements, operating, providing power, other resources. A couple of the other methods we have is the government can provide R&D for technology development, and then turn the actual application of that technology over to private industry, or the private industry can develop it using a product for a government commercial market and be able to tap off of some of the government technology development activities as well. One of the best places you can see this would be extraterrestrial materials development. Right now, the market really isn't there, and the people aren't comfortable enough to go out and develop this. But there's probably enough demand in the future, particularly if you're selling back to the government for operation, say, the lunar base or operation of space transportation systems, that you might be able to put together a deal which would take the government system, develop technology, put together a system, and then apply that to the market. Similarly, there's pure commercial ventures. And I think you can see some of these both in the transportation area, which there's enough mature technology for doing a lot of stuff going on now, or in particularly the communications area where we've got a large base and a large track record in the commercial industry. And if you could skip over to chart 17. The market we're looking at also is not just the U.S. We're talking commercial markets now, you're talking international markets. The European, the Japanese markets, so they aren't as large as the U.S. government, are there. And they're real and they're spending money. Similarly, you can talk about potential participation through some entity through the Russian or the CIS areas. And these could be services, these could be actual products. Similarly, there's a lot of new places you can sell products. A lot of the growth we're seeing in the communications industry is coming outside of the U.S. and outside of Europe. And it's also a place of getting money. As we're seeing with some ventures, the funding sources are very good outside the U.S. We've seen participation both from the Japanese, the Chinese, and also from the European sources on U.S. ventures. In some cases, we've seen more participation by overseas sources than within the U.S. The problem with this is that it's still a little bit murky. I don't know if anybody, some people here are probably tracking what's been currently going on between the Indians and the Russians and the U.S. having to do with technology transfer. See Jordan nodding his head, he's probably been in the midst of that. And when you look at foreign companies, you'll find a large amount of government participation in what is listed as a commercial venture, in which the government will be a large shareholder. The government will be buying the services through a national system. And when you get into the space exploration, you are again going to be probably dealing with some national or quasi-national entity in a foreign area. And there's a variety of international regulations and politics. So you do technology transfer with nuclear proliferation, technology proliferation of various types. And all this really brings it back to being murky. It's an area that we really need to work the rules of the road. It's an area that we need to give a little bit of thought to up front if we really want to make this work. And the last two charts sort of talk about what general actions can we see that might end up driving this. From a national level, as I've mentioned before, procurement reform. A variety of things we can do. The key in here is that we can change the way that we expect to do business in space. Courtney Stead this morning talked about there's a pie right now, which 80% of the pie is the government. We can still use the government as a source of financing and a source of demand, but we can reallocate that pie so that you can get a large percentage of that going through commercial entities rather than being filtered through government agencies. Similarly, we can focus on technology transfer and application systems that are applicable to terrestrial and commercial markets as well as purely governmental. And this is something that may take a little bit of upfront look. Similarly, we need to incorporate commercial considerations in overall planning. All the planning we're doing now, and I've seen in SEO, has almost no consideration of what a future commercial application might be. Now, when we do this, when the government spends money, we have to maximize the impact back on our economy, or else why are we doing this? We have to say if we're going to do this in a sustainable base in space, to make a sustainable market out there, we have to consider those. And further, we have to consider it on an international level since the market out there is international. Lastly, we want to encourage, second to last, we want to encourage commercial participation. And this is early solicitation of getting the commercial guys involved. When we do initial planning and do systems development and technology planning, we have to plan with an idea of what future commercial applications are. And again, including international participation, potential some international competitiveness considerations. And the last one is here is, I believe we have to, from a national perspective, transition to commercial systems and commercial operations of government systems the earliest opportunity. We have a large number of government operations that are operated by commercial entities, basically on a service basis to the government. There's no reason we can't extend this into future space exploration activities. But we should only do this where it's cost effective and makes sense. I personally believe that's about 99% of what's going on out there. But that's an area which we need to get involved in more. And lastly, what can we do as an individual? A little earlier I showed you market history, not projection. It's showing a 25% annual growth in revenues. Obviously, there's potential area for profitable new investments. And there's a lot of opportunities, I believe, for individuals to get involved with this and make some money on it. A lot of people say, well, I can only put a little bit in savings each year or so much in an IRA or something. In aggregate, there's enough people involved in the space industry and enough people involved in space activism to really have a large impact through financial. Fundamentally, an individual investor votes with these dollars. And if you're looking at a 20, 30-year time horizon, I look around this room, there's a lot of guys in this room with a 30-year time horizon before they retire. And that is a long time to build up funds, and in aggregate, you can get some huge sums. And so it's substantial potential investment. Similarly, it's a way to be part of the exploration effort without actually working on it. The problem is there's a need to understand what the commercial aspects of this is. From an individual perspective, there's not a lot of awareness of some of the commercial activities and some of the commercial planning that can be done in the community. And we need to establish better methods of getting information out. And whether or not there's specific investments, investment opportunities, ways of people getting involved in an individual basis in space. And also what type of policies we can promote as an organization to promote individual investments and individual participation. And lastly, this really should be a long-term goal. The commercialization, investment, and future exploration is something that we need as a long-term goal, I think, for our society and also the National Space Society. And I think it's good in general for both us, the nation, and the world. Anybody has any questions?
Next, we have Dr. Bula from the Wisconsin Center for Space and Automated Robotics. Space Automation and Robotics. Sorry about that.
Thank you very much. As I was preparing to give this presentation, I couldn't help but look into the literature for some really profound things that I could tell you. And I happened to run across a reprint of an article that was the presentation by Carl Sagan to the American Physical Society on his award. And it takes us back a little bit into Greek mythology, which I think is extremely appropriate when you start asking someone to project the future in space. He talks about this particular instance where the king of Lydia asked the oracle in Delphi whether he should make war on Persia. And the oracle said, "A great kingdom shall fall." And so he proceeded to make war on Persia, except what happened was that his kingdom fell, not the Persian kingdom. And so when I stand here before you to try to project something in the future, please don't look at me as an oracle from Delphi, or for that matter, the tragedy of Cassandra, who, upon violating some of her agreements, turned out that nobody would listen to her, even though she had a true story to tell them. So I think maybe in that perspective, if you will allow me the next few minutes to tell you a little bit about the program we have at our center, which is based on our conviction that in the not too distant future, we will have a permanent presence on the moon. And it may be there, as you see on that picture, in a science and exploratory fashion, or it may be, as you see in the next picture, an artist's depiction of a great deal of activity, commercial activity on the moon. And it is in this latter kind of attitude that we look at our program at the Wisconsin Center for Space Automation and Robotics. As Jordan indicated to you, we are one of the CCDSs, or the Centers for Commercial Development of Space, and it's our responsibility and our mission, if you want to go to the next slide, to work with industry in a partnership agreement and with government and academia to develop the technologies that will not only allow us to work in space, but to live in space as well. And within that program, we have 3 particular projects, and I'll go over those very briefly and then lead us into what I think are real opportunities for commercial ventures on the moon. In the case of the astrobotics program, which has to do with the development of technologies that will enhance the ability of humans to perform functional tasks required to live, travel, and work in space. And this particular artist's rendition of a person working within the confines of the safe habitat of a space vehicle, or it could be a place on the moon. Compare that with the Endeavour pictures that you saw on TV of the 3 astronauts out there trying to catch that particular satellite and retrieve it. You can understand the ability to live and work in space, and one of the real requirements of doing that is being able to do tasks with such dexterity that you essentially have the machine perform the same tasks that you would if you were out there. In this case here, there is an egg, and if I showed you the second picture, we drop it from there. It is not a boiled egg. And so this illustrates the kind of technologies that our program is working towards, which is part of the infrastructure, as you will see in some of the next pictures down the line, that will be necessary in order to support those commercial ventures on the moon. The second program is the one that has to do with the development of the technologies for a life support system. We are convinced that the life support system that will be the permanent system that will support the permanent presence of people in space will mimic what we have here on Earth. In that case, it does encounter or encompass the kinds of features that are found in this kind of a situation on the moon. And you notice this particular artist's rendition is a more realistic kind of a facility that will be there on the moon, rather than the glass house that you might see in some of the pictures. That particular thick coating, which is about 2 meters or 6 or 7 feet thick, is required to shield biological material from the radiation loads incident on the lunar surface, which our atmosphere and our magnetic field here shields us from the Earth. And so we have then the choice of either carrying up all of the goodies with us as we do on a picnic, or carrying the machinery to make those candy bars for us. And in that case, in that situation, we'll just go through a couple of steps here to illustrate some of the programs that we have going on the development of a life support system, which then will lead us to some of the commercial ventures, which I think are very viable opportunities on the lunar surface. In this case, you really have a major component of that regenerative life support system is the plant growing system, which, if you go to the next slide, is the plants can absorb the CO2 as they do here on Earth. They release the oxygen in the process of photosynthesis, which converts the radiant energy to chemical energy, and in the process purifies water. In other words, we can put on gray water or water with some contamination. The water that evaporates or transpires from the surface of the leaf can be used as potable water. And finally, obviously, we can use that material as a source of food. The third program, which leads us to even other aspects of commercial ventures on the moon, has to do with the recovery of a thermonuclear fuel, helium, an isotope of helium, helium-3, and other volatile materials which are present in the lunar regolith and are very valuable in sustaining operations in space. If I can have the next slide, it will illustrate the kind of thing we're talking about. Here we have a robotic machine that traverses the lunar surface. Doesn't necessarily, we are not hauling material from one place to another. We are simply fluffing up the material, heating it to about 600 or 700 degrees Celsius. And in that process, the volatiles which are present there evaporate and are collected by this machine, condensed, and then are available for various purposes. And if I can have the next slide, illustrate the kinds of volatiles that are present there in that lunar surface, which are very valuable commodities in the support of any kind of venture, whether it be a scientific mission or whether it be an operation on the lunar surface that is a commercial operation. In the first case, there is a sizable quantity of nitrogen that can be collected as a volatile from that lunar regolith, and that can be used obviously for pressurization of the facility, the habitat, but it also can be fixed by nitrogen-fixing organisms and be a source of nitrogen for our food supply. Carbon dioxide is present there, and carbon dioxide, as we indicated in one of the previous overheads, was a raw material for the production of food. Again, it also is a part of the atmosphere that we live in. The other one is water. There is no water present as such on the lunar surface, but when you heat the regolith, the hydrogen there will react with the titanium dioxide to give you water vapor. This is at 600 or 700 degrees C. If you heat it higher than that, you will obviously drive off other carbon compounds such as carbon monoxide and so on. Carbon monoxide is not necessarily a good thing for biological materials, people or otherwise, and so I don't show it on it. But you will also drive off some methane, and methane can be used as a hydrocarbon for their microbial synthesis or synthesis of other kinds of materials, including plastics. And hydrogen, as I indicated, is there, which can be either used directly as hydrogen, can be used to reduce the titanium dioxide for oxygen, or can be used to combine with the titanium dioxide with oxygen to give us water. And finally, the helium compounds, which are both the helium-4, the regular standard helium, or the helium-3. There's a very small quantity or very small ratio of helium-3 to helium-4 in that particular process. And so it's interesting that the discussion that Mike Ryan had centered so much on what is shown here, and that is the transportation costs of transporting materials from here to there, wherever that might be. In the case of the moon, the current estimates are about $20,000 a kilogram. You might use the number of $10,000 per kilogram, but we are in that kind of a range of dollars associated with the transportation of materials to the moon. In that case, if the cost of the volatiles, if we look at the break-even point of what it would cost us to fluff up that ton of regolith or ton of material on the moon, would be somewhere in around $250 to $300 per ton. To give you an example of the kind of commercial venture that is possible, I'll just, because of the time, just use one commodity as an example. We estimate, and I think there's this is a very reasonable estimate, that it's about 20 kilograms of water per person per day. Those of us that maybe take a bath once a month, whether we need it or not, that number may go down quite a bit. But I think we're beyond that kind of hygiene level. So if you multiply that out, that means that in order to support that individual, if you have to transport all of the water from here to the lunar surface, you'd be somewhere in the neighborhood of $70 million. Is it 70 or 700? I can't remember. I got the notes over there. Per year. If that is the case, and we look at the transportation cost here, then in a ton of regolith contains about 23 grams of hydrogen, which can be then converted to water. We can see that our break-even point would be in this kind of neighborhood. In other words, if we could mine that regolith for less than $250, then we could make some money. The current estimates relative to the helium-3 program, which has gone through this kind of a process very thoroughly, we feel that a large mining operation of the nature that we're talking about could move and fluff up and collect the regolith, collect the volatiles in that regolith for somewhere between $5 and $10 a ton. Now, the number that I'm giving you here is much more tenuous than the number in terms of the amount of water that a person needs, the amount of food a person needs, the amount of CO2 that has to be degraded, and so on. And so I think in terms of life support situations, there are opportunities for establishing a utility type of operation. And again, it's interesting how some of the things that Ryan was talking about, some of the things that I'm referring to here, sort of dovetail together. It's almost as if I listened to his talk before he gave it, or he listened to me before he gave it. I don't know which one it is. But in any event, I think there are these kinds of requirements that are going to be needed when we have a permanent presence on the moon. We simply cannot afford to put people into space and keep them in space by resupplying all of those requirements from Earth. We really need to utilize the resources that are out there. We know that the moon and other parts of the solar system have very valuable resources. Our job really is to develop the technology that industry can take and use to reduce the costs of having a permanent presence in space. And not only that, but increase the quality of life here on Earth. I have not said anything or very little reference to helium-3 because of the time constraint. But here is a commodity that when brought back to Earth could be an extremely valuable commodity here, improving the quality of our life here on Earth, not just out there in space. Thank you very much.
Thank you, Dr. Bula. It's very interesting. Is there any questions that anybody has for either of our panelists?
I heard Dr. Kulczynski speak shortly about helium-3, and do you happen to have the annual value of helium-3 that we're used to supply to this power supply?
Yeah. His analysis indicates that 20 metric tons of helium-3, when used as a fusion fuel, could replace all of the fossil fuels that the U.S. uses to generate a year's supply of electricity. And I don't remember what year this was, but it was maybe like 89 or something like that when he made that estimate. And that estimate was based on the fossil fuels that are used by the U.S. electric industry was about $50 billion. So that would mean a shuttle load of helium-3 would replace the fossil fuels that we use for generating electricity in this country, another load for those in Western Europe, another load in Eastern, the Pacific Rim countries, and then another load for the rest of the world.
So it's $200 million a year.
Yes. And when you look at that in terms of the quantity that is there, again, Dr. Kosinski, who is the technical director of the Astrofuel Project and professor of nuclear engineering, who has done most of this, who's led this activity, has a map of the moon, and he shows an imprint of the state of Wisconsin on the Mare Tranquillitatis, which represents the area that would have to be mined to provide this for about 500 or 600 years.
That's about the size of Wisconsin.
Well, I have questions regarding helium-3, and since we're talking about commercial opportunities and so forth, and there's no doubt that utilization of helium-3 in fusion reactions would be very worthwhile, but it begs the question of when are we going to have fusion reactions that can take advantage of helium-3? How far are we? How much will it cost? You know, we've spent billions of dollars. Well, I don't know if we've spent billions of dollars, but we've spent hundreds of millions of dollars since World War II looking into this problem, and we're still, like we were in 1945, 20 years away from practical fusion.
Yes. That's a very, very good question, and it's sort of a chicken and egg situation. If you don't have in other words, a nuclear physicist really identify about 5 different fusion reactions. And helium-3 deuterium has always been in the books. And it wasn't until the relationship was made in about 1985 that the Apollo samples, or the samples collected by the Apollo missions and the Luna missions, in fact, identified helium-3. So now we, for the first time, recognized a volume or a quantity of helium-3 that would really satisfy this kind of a requirement. The only helium-3 we have here on Earth now is from the decay of tritium in the nuclear weapons. And that is enough to do a research program, but is not enough to sustain an energy kind of activity. And so most of the fusion research was centered on tritium deuterium. And it is my understanding that the nuclear physicists could have had a tritium deuterium sustaining reaction 5 years ago if they would have chosen to do so. But if they did so, that would have meant that their reactors would have been poisoned so that they couldn't do any future research. And it wasn't until last year when the director of that particular lab in England decided to retire that they did fire up their fusion reactor to the point where they did get a sustainable reaction. The Princeton people could have done it several years ago. Now, that doesn't reflect one other very, very important consideration, and that is that the physics of a deuterium helium-3 reaction or helium-3 deuterium reaction is much more rigorous than the tritium-deuterium reaction. And so if you plot the line of how we are progressing in there, we are progressing really very, very rapidly. And if that progress is linear, we're probably, what, 5 years away from now? If it's non-linear, if it's asymptotic, who knows? So in a way, I think what we really are not, and that's one of the reasons why I did not make helium-3 the center of my presentation, because I think there's other valuable reasons for going to the moon, and there are other very valuable commercial ventures. That can be a very significant one if the two meet.
Thank you.
What about the titanium that's released when you react the hydrogen with the oxygen?
Well, it's a very valuable commodity. There are a number of things that we, as I said in my closing remarks, the moon is a tremendously valuable resource. And one of them is the titanium. We could use that for a number of different purposes. I didn't touch on, for example, the possibility of collecting solar energy and beaming it back by microwave. I think that's another real possibility. So I think there are a number of resources there that we need. What we in the Centers for the Commercial Development of Space envision is developing sufficient proof of concept missions based on a partnership of NASA, the federal government, other parts of the federal government, industry, and academia to establish whether these kinds of things are realistic or not. How would we use titanium? How can we use it? How valuable is it? How easy is it to get there? But we do know that the dissociation of titanium dioxide is much less rigorous than the dissociation of iron oxide. There are a lot of iron oxides in there also.
Any other questions?
Do you have any kind of model of what it would cost per pound using your astroculture systems to raise food on the moon as opposed to having imported? You had some models there. Have you done some economic modeling of what an atmosphere module would produce and what the total cost of that package would be, and how much per pound for carrots that way as opposed to 25,000 per pound?
There were some trade-off studies done by the Boeing Aerospace Company in late '85, and I can't remember those numbers offhand, but the crossover point is anytime you have more than 4 people in space for longer than 3 years, you're going to benefit by a recycling system. And the tighter you close those loops, the more benefit you get. In other words, the tighter you close the water loop, the tighter you close the air loop, the tighter you close the food loop. And I don't expect that we're going to close at 100%, but I think on the moon we're going to have to come up with close to 90%. And so I can't answer your question directly, other than indirectly, but I know that in that report that Boeing Aerospace made, some of those numbers are there, and I can give you the reference to that.
Any other questions? Okay, thank you, Walley McClure, Dr. Raymond Bula. Thank you for joining us this afternoon. This concludes our commercial space opportunities track for today.